of DC motors. We will see what is the different types of DC motors are there. Okay. So as we are discussed in the case of the DC generator, so construction wise there is no difference between the DC generator. Okay, construction wise DC motor and DC generator, no difference. Okay, generator and motor, no difference between them. So we are already discussed this point. Now let us come the types of the DC motors. In case of DC motors also, as we are discussed in the case of DC generator, here also we have the first one is separately excited DC motor and another is self excited. In case of self excited, we have shunt motor and series motor and compound motor. So three motors will be there in case of DC motors also. So let us come one by one. So let us take the first, what is the separately excited DC motor. So in case of separately excited DC motor, the field winding is separately excited. Okay, separately excited DC motor. In case of separately excited DC motor, the field winding was excited separately. The field winding is excited separately here. So like this we are connected, and we have the armature will be like this. So here it is separated, the armature, and we have the load is connected here. So sorry, here it is not load because we are discussing about the motor. So you will have the supply here. Okay, we will give the electrical energy for the DC motor. So if we will give the electrical energy, so first it will give the IL, and the same current is flowing here IA, and here the field current is IF, and you have the variable source for the field resistance. Inside this we have the back EMF, and here the terminal voltage you are applied. So let us write the equations. What is the equations here? EB is equals to, we can write as V minus IA RA minus brush drop, multiply IA on both sides is equals to V into IA minus IA square into RA plus IA into B brush drop. Okay, so this is the equation we have to remember in case of the separately excited DC motor. Next, consider the another motor here. So let us consider self excited DC motors. Let us consider self excited DC motors. In case of self excited DC motor, first we will consider the shunt motor. We are already know what is the meaning of the shunt motor here. Shunt motor means here the field winding was connected across, that is connected in parallel with the armature. So it is connected in parallel with the armature. That type of motor we can call it as the shunt motor. Here we have to give the electrical energy as the input. So first we will give the electrical energy, that is the IL, and here that is armature current is flowing, and the field current is IF, and it is RF. Next it is the back EMF is here VB, and V is the terminal voltage. Let us write the terminology what I am using here. Here IL is known as the line current, it is not the load current. Okay, IL is known as line current because you are giving the supply here, so it is known as the line current. Next, ISH is the field current, or here we have written I think so IF. Okay, ISH or IF. In some textbooks they will write it as ISH, in some textbooks they will use it as IF. Next, IA is the armature current. IA is the armature current. Next, V is the terminal voltage. V is the terminal voltage applied. V is the terminal voltage applied or supply voltage given, and EB is the back EMF. EB is the back EMF of DC motor. This is the different terminology what we are using in the case of the shunt motor. So if you write the equations of the shunt motor, so let us write the equations. So if you write the first ISH is equals to V by RSH, this is common in case of DC generator and DC motor. And let us come for the line current. IL is divided as IA plus ISH. So once again you apply the KCL at this node A. If you apply the KCL at this node A, so IL current is entering and IF as well as that is ISH, IA is leaving from the node. So IL is equals to IA plus ISH. We can write the armature current as IL minus ISH. And the back EMF is given as that is equals to V minus IA RA minus brush drop. If you multiply IA on both sides, you will get it as EB into IA, V into IA minus IA square RA minus IA into brush drop. So you know already what is this net mechanical power developed. So what is this net mechanical power developed here. Next, V into IA is the electrical power input, that is the electrical power input. Next, IA square RA is the copper losses. Actually particularly we will call it as the armature copper losses, we can say. Next it is IA into brush drop is brush losses, brush drop we can say. So if sometimes in the problems they will not give the brush drop, you can neglect. If it is given, you have to consider. So here let us understand the terminology. Here the net mechanical power developed, that means from the armature only we are taking the mechanical energy from the shaft. Okay, that is the output power we are taking. Next, what is the next one? Electrical power input. So what is electrical power input for the motor? It is, so that is IA into EB only. Is it right or not? IA into EB is the electrical power input for the armature, and IA square RA is the armature losses, and brush drop is the present in brushes in the case of the DC shunt motor. This is the different equations we have to remember. Next, let us consider another motor, that is series motor. In case of series motor, so we are already know that in case of series motor, if the field winding was connected in series with the armature, if the field winding is connected in series with the armature, that type of motor we can call it as the DC series motor. So let us see the terminology here. Here this is the RSE and the line current IL is flowing here, the terminal voltage V, and the back EMF is EB, and the same current is IA, and here it is ISE is flowing here like this. Okay, this is the series motor. In case of series motor, we can observe, first observation is what we can see, the line current as well as the series field current as well as the armature current all are equal, let us say I, because all are connected in series. So that's why we can say it as line current is equals to series field current is equals to armature current, that is equals to I here. Next, write the equation of the back EMF. If you write the equation of the back EMF, we will get it as V minus IA into RA plus RSE minus brush drop, So multiply IA on both sides. If you multiply IA on both sides, we will get it as V minus IA square RA plus RSE minus IA into brush drop. This is known as the, so EB into IA is known as the, what is that, mechanical power developed. That is what we are taking from the armature. We are taking from the armature, that is the mechanical power developed. And what is the input is given, that is IA into back EMF is the input given, and armature copper losses as well as the series field losses also, because we cannot neglect the series field losses in case of series motor, because it is having the high resistance. Okay, so because it is having the low resistance, it is drawing the more amount of current, so we cannot neglect the series field losses also. So IA minus IA into brush drop, and finally that is the brush drop. These are the different types of DC motors are there. And let us if you see the equations of DC compound motors also, I will explain in the next video. Okay, that is not that much important, we will see in the next video. Let us understand what are the characteristics of, what is the characteristics of DC motors, what are the different types of characteristics of DC motors we are going to study. First of all, what is the necessary to study this characteristics, what is the need to study this characteristics. So electrical students, they are going to do this characteristics of DC machines. What is the necessary to study these characteristics is to find the applications of different motors. To find the applications of different motors, we are going to study this characteristics of different DC motors. That is the purpose why we are going to study the characteristics of DC motor. So what are the different types of characteristics we are going to study in case of DC motors was speed versus armature current, second one. Next, torque versus armature current, third one is speed versus torque. So first two characteristics are called as electrical characteristics. First two characteristics are called as the electrical characteristics. Next one is called as the mechanical characteristics. Next one is called as mechanical characteristics. Here, so electrical characteristics, why it is called as electrical characteristics? If you observe here, so in this characteristics you have the armature current, so that's why it is called as the electrical characteristics. If you observe this mechanical characteristics, you have the speed and torque, both are regarding to mechanical properties only, so that's why they are called as the mechanical characteristics. Before going to study these characteristics, we need some equations to be remembered. So we remembered in the last video, that is the armature torque is given by phi z into Ia, so P by A. This is the equation we are already taken. And another equation of the back EMF is phi n z by 60 into P by A. With these basic equations, we are going to study what are the different types of characteristics. So if you observe, once the machine is designed, the armature torque will be directly proportional to product of armature current and the flux. If you observe here, once the remaining all the terms, so if you observe, n is equals to, so let us take out n. Here 60 is constant, P is constant, A is constant, and the number of conductors is also constant. Once the machine is designed, so EB divided by phi, we can write n is proportional to back EMF and inversely proportional to flux phi. Okay, right. So let us study the different types of characteristics of DC motor. So in this characteristics, first we are going to study DC series motor characteristics. DC series motor characteristics. In case of DC series motor, we are already seen the field winding was connected in series with the armature. So that is what we are already know, in series with the armature it is connected. So V is the, and I already explained IL, ISE and IA all are equal here, and this is the back EMF. In case of DC series motor, the armature torque is proportional to product of Ia, but flux is also proportional to Ia only, because they all are connected in series. In case of this, Ia is equals to ISE is equals to IL, so that is why flux is also proportional to Ia, so armature torque will becomes the proportional to Ia square. Once the saturation is reached, that means once the saturation, we are already discussed, once the saturation is reached here, let us come here, saturation means once the flux is becoming a constant, so saturation reach, at saturation we can say the condition, at saturation condition the armature torque is proportional to armature current only in case of DC series motors. And let us come the speed is equals to back EMF divided by flux phi. So back EMF we can write that equation as V minus IA into RA plus RSE divided by phi. This is the equation of the speed. Let us see. So if you increase, if you see this drop, if you see the drop of this IA into RA plus RSE, it is get less affected compared with this terminal voltage. So that's why what we can say, so the speed will be 1 by flux is proportional to IA, so speed will be proportional to IA. So whenever IA is increased, the speed will be decreases. Let us understand, let us draw the different characteristics now. So if you draw the characteristics of DC motors, first we will draw the torque versus the armature current. So if you draw the torque versus armature current, so torque versus the armature current, so it is increasing like a parabola. It will follow a parabola curve for DC series motors. So whenever you have the shaft torque, the shaft torque will be also increases like this. This is called as the shaft torque. So why we have some difference? This difference is known as the, what is this difference? That is the loss torque in case. So this is the armature torque is proportional to Ia square here. So this is the characteristics of DC motor, that is torque versus armature current. Let us draw another characteristics of DC motor, that is, what is another characteristics here? That is speed versus the armature current. Whenever, so we are already given the equation, speed is inversely proportional to armature current. Whenever the armature current is increases, the speed will be decreases. It will follow like this. Okay. Next is, let us see the characteristics, another characteristics, that is speed versus torque. Here. So what is the characteristics here? As the speed is proportional to Ia, so as the torque you already know it is proportional to Ia when it is reached to saturation, the speed also inversely proportional to the torque. So whenever the torque is increased, let us draw the speed and the curve will be like this. So it will be decreases. These are the different characteristics, or we can say right like this, TA is directly proportional to Ia square. Is it right? So N is proportional to 1 by Ia. So what is Ia from this equation? Ia we can write it as under root of TA. So N we can write it as inversely proportional to under root of TA. Like this also you can understand. So speed and the torque will be inversely proportional. Let us see what are the applications we can. So when you observe this characteristics, so when the load is less, when the load is also a less, that means when the torque is very less here, but the speed if you observe is very high. Okay. So for this, so we can say which, so that's why as the speed is very high at no load condition, so series motor should not start. Should not start at no load conditions. No load conditions. So sometimes they may ask this question, okay, why the series motor should not start at the no load condition? Because at no load condition the speed was very high, even though the torque was very less, the speed will be very high. That's why we have to start always the series motor with the loaded condition only. Next, another important point about this series motor is it is having high starting torque. So the type of applications which is required for high starting torque, so we can go for this type of DC motors, that is armature torque is proportional to Ia square. This type of applications we are going. What are the examples for these applications is electric trains. So we are seeing the electric trains. Okay. Next, cranes, hoists. So for this type of applications we are going for the DC series motor. Next, let us see the characteristics of DC shunt motor. If you see the characteristics of DC shunt motor, first let us understand what is a DC shunt motor. So in case of DC shunt motor, the field winding was connected across in parallel with respect to the armature like this. So we are applied, the voltage is applied like this, and the current you already know the terms, already we are given that. So let us write the equations what we are going to use here. So the armature torque is proportional to the product of phi into Ia. In case of shunt machine, flux is constant, because once the machine is designed, this field resistance we are not going to change, that's why the flux is constant. So the armature torque is proportional to Ia only. That is the first equation. Let us see the equation of the speed. Speed is Eb by phi. Phi is already constant we told. So N is proportional to V minus Ia into Ra. Compare this drop will be very less compared with this terminal voltage. So what we can say, so whenever you are increasing the speed, so what will happen, armature current, so what will happen, the speed will be decreases. Here the direct relation is there. We have, whenever you are increasing the armature torque, let us see, whenever you are increasing the armature torque, this negative terminology will increases, so that the speed will be decreases. Okay, direct relation is there. Now draw the characteristics of DC shunt motor also. Let us draw the characteristics. So if you draw the characteristics, first is torque versus the armature current. So whenever you are increasing the armature current, the torque will be increases like this. This is a linear curve. So whenever you want to get the shaft torque, so how you will get the shaft torque, there is some difference will be there. This is the shaft torque and this is the armature torque. Okay, next let us draw the another characteristics, that is the speed versus armature current. Whenever you are increasing the armature current, what will happen, the speed will be decreases, the curve will be like this you are going to get. Next, whenever you observe here, so the speed, so as the speed and the armature current are inversely proportional, torque is also inversely proportional or not, sorry, here the curve will be, I forgot, here the curve will be, here you can see. So whenever it is at no load, it is maintaining a constant speed actually, but because of the, so there is a drop will be there, because of the drop, that is the friction and windage losses, the speed will be decreases. So what will happen, that is 5 to 15% of change will be there in case of this. So we cannot see much change in case of the armature current increase also. That is another characteristics. Now let us see the another characteristics, because you are going to get the same characteristics, speed versus armature current. Why I will explain. The armature current is proportional to Ia and speed is also proportional to V minus Ia Re. So these are also inversely proportional, so and the directly proportional to armature torque. Okay, so what will happen, so whenever you draw the curve between the speed versus the armature torque, so what you are going to get, because the speed is constant, so initially the speed was a constant, but whenever you are increasing the torque, what will happen, the speed will be decreases. What is the increasing of torque means, you are increasing the load. So whenever you are increasing the load, what will happen, increasing the load means the torque, increasing the load means the torque is increased. So what will happen, the speed will be decreases. So because the speed is decreases, once again it will draw more armature current, that is why it is known as the self-controlled device. These are the different characteristics of DC shunt motor and shunt generator. So let us summarize the characteristics of DC shunt motor also. So machine operating under no load condition. So under no load condition also it is maintaining, under no load condition, maintaining a constant speed, maintains constant speed. So that applications we are going to use this type of motor, that is the shunt motor. Torque requirement is less, torque requirement is less, and speed is constant. For this type of applications, we are going to use this what DC shunt motor. Examples for this is, one is fans, machine tools, okay, fans, machine tools, lathe machine, next woodworking machines, woodworking machines. So this type of applications we are going to use the DC shunt motor. These are the different characteristics. That's all for today's class. In the next video we will see the problems what are asked in the previous papers of VTU. We will see in the next video, which is very useful for your external exam. If you are seeing first time this channel, please like, share and subscribe the channel. Thank you very much. If you have any queries, you can comment, so I will answer for that queries. Thank you very much.